The idea behind the Exascale Chat is to get away from panel discussions where everybody is positioning great ideas in 10 minutes of PowerPoints that take 20 minutes, and there's no time for conversation and question and answer. And instead, we would like to have a talk show, so to speak. So we actually will have a live webcast of this. So yes, you have a live audience, not just a live audience here in the studio, I'd like to say, but there's an audience out there on the World Wide Web. I instructed my guests not to prepare anything except being prepared to answer some questions and engage in a conversation. So this is slightly scripted, but hopefully very spontaneous and hopefully also very entertaining. So with those introductory words, I'd like to move over and turn myself into your host, and then we'll start the chat. So I'd like to ask you to welcome our guests with a round of applause as they come on the stage. And I'd like to introduce our first guest, Chris Bischof. I know Chris Bischof for many, many years, 25 years. We met at some SIAM conference talking about linear algebra. He is one of the European thought leaders in terms of software and also in terms of using supercomputers in education. He has worked in applied linear algebra, automatic differentiation, but is interested in how to write software for exascale computers, for high-performance computers. He is now director of a supercomputing center in Germany at the Technical University in Darmstadt. And consequently, he is very much interested in HPC in education and also how to make a supercomputing center useful for research on a broad basis of applications. So welcome, Chris. So Chris, you just recently moved from Aachen to Darmstadt, and to be quite frank, Aachen is a university that has a long history in high-performance computing in Germany, hosted many top 500 sites. And Darmstadt is somewhat, I'd say, a white spot on the map of HPC in Germany. So tell us what made you move there and what do you hope to accomplish and what things keep you awake at night?
Okay. Well, so first of all, I'd say Darmstadt is a place that has a lot of potential. So first of all, it's a technical university that actually has taken HPC more seriously than you might think. They've had an installation over the last one is an IBM Regatta system. And the use has been mainly driven by engineers. And what the university has realized, and that's actually the reason why the head of the computing center has been upgraded to professorship, which wasn't one before, is that they have to align science with computing. And that's the reason why I went there, and I thought this was really interesting. We're in the middle of a procurement, 15 million euros, which for a university is, I think, rather respectable number. And we want to turn that into a tool to really get the users we have now, for example, in material science and engineering and physics, up to the level that they need to support their science, and in particular, to get new people interested in high-performance computing. And that's really what I'm mainly interested in.
Let me jump on that topic.
Yeah.
New people into high-performance computing. On Monday morning, I think several of you may have been at the IDC analyst briefing. And IDC had a very intriguing report on the lack of talent in high-performance computing. And they found out that all supercomputing centers, the best source of finding new employees is your colleague's supercomputing center. So that's a zero-sum game. We got to bring new people into the environment. And this seems to be not just European or American, but it seems to be a worldwide problem. So how do you get young people to get into supercomputing as opposed to writing apps for iPhones or Android?
Well, I think there's a couple of issues. So one thing that I think is really not good, if you look at the curricula, for example, of computer science programs in Germany, they will not be educated in parallel computing. So you get a bachelor in computer science, and you walk out the door not being educated about parallel computing. Now, of course, any device that you will get your hands on later on to program, and there is actually computer scientists who make their money programming, will be parallel computers, starting with the iPhone for which you write the apps, up to the machines we talk about here. So one of the things I'm trying to do is get that at the base level introduced, and in fact, where that has been successful is some programs for computational engineering science. The reason being they are new, they have been designed at a time where it's clear you needed parallel computing, and you didn't have to kick somebody else off the turf. So there have been some partial successes. So that's number one, basically catch them young. That's the answer to that. And the other one is to have really educational programs for the scientists as they realize that simulation science is something that brings them forward. That happens sort of at the big sites. For example, PRAISE has training programs. PRAISE will introduce some advanced training centers now. But also at the university level, we're starting now with more bring your own code workshops. That's something that I did with great success in Aachen with the help of Dieter Anmay and his group. And this way, you can sort of demystify parallel computers. A lot of people think parallel computers is something for these physics people or these engineering people, but nothing for them. And once they realize that, hey, it's just a cool tool that I can use to bring my science forward, then it's actually relatively easy. But the perception is still, it's sort of far out for many of them.
Let me interrupt and say, well, maybe the perception is right, which leads to my other topic, and say the perception is maybe right because these are still very difficult to program systems. And it's very,
that's true.
And so what progress have we made in developing software for HPC applications or making systems easier to use for the average engineer and scientist?
Admittedly, little. I mean, when I started out at Argonne National Labs, Jack Dongaro, who's here, hired me as a postdoc fresh out of Cornell, working on the LAPAC project. When then parallelism came to play, well, we had something that looked in many instances similar to some of the basic features we have in MPI. Okay, now MPI is a great sort of base layer, but to me it's really more sort of a compiler target, right, than something that you really want to write. I'm actually hopeful now that things like an OpenACC, which basically makes accelerators easier to use, will get people to program parallel devices, and in particular parallel devices that they have easy access to. And this, I think, will open the mental sort of wall, and they'll look beyond that. But the other thing that I also see is that in computer science, there has been very little research with respect to more productive programming languages. We've got the PCAS languages, which I think are well established with respect to sort of the work that's being done, but adoption is kind of slow, okay, when you look around. And maybe one way to get out of this hole is to look at more domain-specific programming abstractions, where by virtue of the fact that you know something about the domain that you're programming, you can automate more of the translation process to a sensible parallel program. And I think this is a really interesting computer science question. And I think that'll alleviate some of the software gap.
Okay, well, we'll come back to the topic of software probably later in this conversation. So I would like to introduce my second guest and welcome Yutong Lu. She is the designing director of the Tianhe 1A system, which was the #1 system, is now the #2 system on the top 500 list. And that is now, of course, still the #1 system in China. Is indicative of all the great developments of supercomputing in China. And so we're very pleased that she decided to come here and tell us about her work and how supercomputing in China is progressing. Welcome. Thank you. I would like to ask a question that is not scripted, and I hope you don't mind, but how do you become designer of a supercomputer with more than a petaflop compute power in a country that did not have, until recently, a tradition of building supercomputers? How did you prepare yourself for this big job, and what did you do previously?
I have not prepared about that. I think it's a natural thing. I not do some especially prepared to the work. I joined this work is after I graduated. In fact, I'm a native, NUDT native, in the bachelor degree, master degree, PhD degree, all in the NUDT, and then work for the HPC system research and development. I think it's a nature for me. It's a very natural thing for me to join a huge project. Yeah.
Very good. So, of course, everybody is was very intrigued by the success of Tianhe-1A, and so I was wondering, what is next? What are you currently working on, and what things keep you busy?
After the petaflop system emerged in China, the first petaflop Tianhe-1 system in 2009, and then the Tianhe-1A in 2010 got the top one. After that, I think the HPC in China now, we focus several things. The first one, I think it's we want to use the already existing petaflop system more efficiently. So now we still put some efforts to exploit the Tianhe-1A systems to suit the application performance, to improve application performance and encourage more and more applications. And also we are supported by the China government, the Ministry of Science and Technology and NSFC. They also launched a serious project to support application, the basic application algorithm and the models to encourage more applications. And another thing is we still to pursue the higher performance next generation supercomputer. In fact, the Chinese government have launched a new project for the next generation HPC system. Maybe at the...
Yeah, I'd like you to tell us a little bit more about this.
Yeah.
So I heard there are plans for 100 petaflop systems in the works.
Yeah. The project is that it launched at the fourth quarter last year. And in fact, there are maybe several units, including NUDT and another 3 or 4 institutes and companies to complete this project. Fortunately, NUDT have got a grant. So we started the project at the first quarter this year. The detail about that is we collaborated with the local government of Guangzhou. Maybe some of you know that it's in the South part in China. And this city is also the 3rd largest GDP in China. So because the local government also involved some funding to these projects. Yeah, so the goal is to develop the 100 petaflop system around the end of the Chinese 12th 5-year plan. It's around 2015.
2015.
Yeah.
So that's an ambitious goal. We certainly will see you back here to hopefully talk about the success. I'd like to find out a little bit more about HPC in China. What we know and what we see is numbers, statistics, systems being built. But can you tell us a bit on how you think, by observing the conference, visiting the US or visiting Europe, how you think that the high-performance computing environment is different in China from the way we approach it?
Yeah, I think in generally the goal between among each countries in the world to pursue the high-performance computing is the same. And we also met the common issues. But still, it's some difference between China and the West. I think the first thing is China is a developing country. So when we choose the HPC development strategy, for example, when NUDT to design a new HPC system in the past, we did several generations of a supercomputer, domestic supercomputer in China. We consider the first thing is the cost, the availability. So our principle is the usability and the practicality. So we usually use relative mutual technologies, and we focus on the optimization and the customization of the system, because there are huge population in China, and the human resources is relative cheaper than the West. So, and another thing I think is application development level. We are maybe behind and compared with the US and the EU. So in China, especially recent 5 years or 10 years, it's HPC system leading the application development. Like maybe it's a different situation between the US and the EU. Yeah. The final thing I think is also related to the application. In China, you know, the supercomputer center, for example, in Tianjin and in Changsha or in Guangzhou, now we, besides the science and technology computing application, we also need to focus on the other things such as data analysis and some information processes. So this requirement is also, we also asked by our end users to why the supercomputing center couldn't deal with such things. So we may face some more complex application situations. Yeah.
Very good. Well, I would like to ask about application, but we'll do this later. And I would like to now introduce the third guest for this afternoon, Mark Seager. And I was trying to think, I think I know Mark about 1 or 2 years longer than I knew Chris. So he's a good old friend who for many, many years was a colleague in the Valley in Livermore, and he recently joined Intel.
Thank you.
So welcome, Mark. Thank you for coming.
I'm glad to be here.
So I will ask my first question anyway, because you know what it is, but you have to watch out because Donna is in the audience. I wanted to ask you, so you just made a big jump from, I mean, I know and Chris knows the government labs in the US, and they have a certain culture, and you went in one way to almost the extreme other side. That is, you joined a very dynamic, growing vendor such as Intel, and so tell us about your job at Intel and tell us what's different and what's the same between Livermore and Intel.
Well, let me start with what's different and what's the same. There's Intel, there's a huge passion for the technology and for impacting people's lives. And that was also the mission at Livermore, and you know, our stockpile stewardship mission and national security and energy missions were always a very motivating factor for me. So it's always really great to be part of an environment either at Livermore or at Intel where people really care about, you know, what happens to the technology after they create it and the impact that it has on society. So in that way, it's very similar. You know, one of the major differences was that at the labs, you know, most of the people you work with on a day-to-day basis are in the same building, and you have face-to-face meetings. At Intel, most of the people I work with are distributed, you know, across the U.S. and across the globe, and so it's mostly telecons and stuff. So it's definitely a slightly different culture, and it was a shift to get used to that. But it's a lot of very interesting people to work with, a lot of problems to solve, and the excitement at Intel is great.
Great. So it's actually now, it's a difficult question, but since you're now an outsider and can look from the outside in, where do you think we are in terms of the Exascale initiative in the US and the efforts to move us as a community closer to Exascale?
Well,
and please be candid. That's why I invited you.
Yeah, no pressure there. So yeah, I was on the inside and I got to watch the sausage being made for many years. It's interesting to be on the outside and watch the reaction as that sausage is being made now. But we're transitioning in the U.S. The Department of Energy is moved from talking to actual action, and the first action there was a fast forward RFP that was recently on the street, and so that is we're looking at that at Intel as the on-ramp to Exascale as the first step of the DOE, showing that the two programs inside of DOE that are sponsoring Exascale can work together and can have an impact on industry and the HPC in general. So I think it's a great move forward. We're very excited about the possibility of future Exascale funding and moving that forward. So I think the way I like to look at it is that, we're moving from talking about it only to actual action.
Very good. So you just said about Intel being a truly international company, and you have partners and collaborators everywhere.
Yes.
So I know that probably every university is knocking at your door and is looking for joint research programs and interesting way of working with Intel. In this sort of global oversight that you have about research, what were the most exciting recent things that you found in terms of potential new technology that's of value to Intel or that's of interest to Exascale?
Well, there's a lot of interest in the universities in programming models. That was a topic that came up earlier. Everybody realizes that MPI plus something has had a very long and productive career and will probably continue having an impact up into Exascale. But at some point, when you're talking about a billion-way parallelism, that model probably breaks down. And so I'm excited about the opportunities for innovation there. The other areas in the application area and the strong change that we've seen over the last 10 or 15 years in academic institution. I think you touched on this earlier, where it's no longer science was just theory and experiment. It's science is theory, experiment, and simulation. There's a triad now. And world-class universities are realizing that they have to reorganize. They have to have multidisciplinary teams that include a high-performance computing area. And one of the most exciting advents there is that in the biology area and genomics and chemical design area, people are starting to wake up to the fact that there's really low-hanging fruit available in those disciplines now that we have petascale and soon to have exascale. So there's a lot of drive, a lot of excitement on the application side.
So since Mark mentioned application, let me jump to that question and see if Chris and Yutong have some idea. Are there any exciting new applications out there that may actually be catalyst for getting us to exascale in a sense, something that's out of the ordinary? I mean, you mentioned the economic impact and working in the Chinese environment on other things, and there may be interesting things that's come out of the educational world, ideas that students have. What's new in application? I mean, Mark mentioned biology as an example.
I'm not an expert in application, but I think if I choose this a molecular dynamic, I think. Yeah, because by the situation now, the application running on the Tianhe 1A, the heterogeneous, the hybrid system, some application including bio and energy and the material. Many application models use molecular dynamic, so I choose this one.
Mm-hmm. Any ideas, suggestions?
I don't necessarily want to. I mean, at the university level, we're away from the exascale. I mean, if we get sustained petascale at some point, I think we'll be very happy. But to give you an idea of some projects that I'm involved in now, one is dealing with our security group, talking about new methods for cryptography, because current computers have developed to the point that it's within 10 years down the road, we can break the current methods that, for example, are used to sign software updates. Which means then, if you can break those, then you can't update software anymore. That's kind of a problem. So I'm involved in a project where I'm, in essence, supposed to assess what computers can do down the line and what kind of cryptography algorithms do we have to develop in order to have Again, safe signature methods. Another one, and that's not having to do with petascale, but I think it draws on this issue of multidisciplinary in a different way, is I'm talking to a fellow who is trying to figure out how carbon nanotubes function. And carbon nanotubes are really quite amazing things. They have a recursive 3D structure. It's really very intricate when you look at them, very beautiful. So he's written this, he's developed basically an algebra to model the topology, and he's written a program that then generates the 3D structure. And from that, he generates points, which he writes in a sparse matrix and throws across the fence to some linear algebra solver, completely oblivious of the structure that he just had. And then he hopes that he gets a good linear algebra routine to solve that, okay? And that to me is, when I heard about this, I said, you're not using that structure that you had before in doing linear algebra. I said, no, I don't know how. I said, well, let's talk. So these divides, okay, where structure information gets lost, I just gave you an example. I think this is one of the big hindrances towards petascale, towards exascale on real applications. To some extent, it's still the balkanization of science. We talk about interdisciplinarity, but when you actually try to position a proposal that's truly interdisciplinary, you end up in panels, whether it sits fraction A with fraction B, they don't fully understand what the other person is talking about, and before you know it, you have a problem. So really getting interdisciplinary appreciated and going, that to me is a necessary requirement for having exascale really drive science.
So I want to ask to focus a little bit more on exascale, another application question. So we all been talking about exascale and exascale applications, but I want to sort of nail this question up to a very precise answer. What do you think will be the first exascale application, let's say, that will win the Gordon Bell Prize because it has a sustained application performance on an exascale platform? Any guesses?
Yeah, molecular dynamics.
Yeah, QCD, I'd say.
Quantum molecular dynamics.
Yeah.
Well, that's what I would have voted for. I guess the reason is it's probably the only application that it requires just enough memory, so that
exactly.
Everything else will require so much more memory, so we won't be able to afford it.
Yeah,
possibly, unfortunately.
Well, but the good news there is that a lot of those types of calculations that have won the Gordon Bell Award have actually been scientifically relevant,
yes,
right?
Absolutely.
I mean, it was breakthrough science as well as breakthrough computational science. So it's not all wasted.
So I would like to continue on this topic. So I think there are, my real concern about exascale computing is the amount of memory that will actually be available, and that the lack of having a large amount of memory on an exascale platform presumably will limit what we can do. So have you seen anything in terms of memory technology which would sort of be more encouraging, and I wouldn't have to be so pessimistic? Or maybe you have to wait for the talk by Samsung later on to hear.
Yeah, I think the B to F ratios, the bytes per flop, both in terms of capacity in particular and bandwidth are definitely continuing their downward trend. It's just the nature of the Moore's law curves for the two different technologies. And the fact that the memory industry has kind of been distracted now with phone and tablets and memory, flash memory technology. So that's actually the leading edge process rather than DRAM. So those combined are kind of a pessimistic view. But there are new innovative 3D stacking technologies of putting memory in stacks and then putting that stack nearer to the processor that are breakthrough, and those are been talked about in the industry and are on the verge. Some of that stuff is already in phones, but in terms of what phones need and what HPC needs, the phones need low power, low density, not much bandwidth. We need very low power, very high bandwidth and density, so we go higher stacks. And so there are significant challenges to overcome, even though we're riding the phone technologies there. But it's a one-time get-out-of-jail-free card, essentially, to move memory from DIMMs to hybrid memory cube or stacks on nearer to the processor.
But then we're on the same curve.
Then we're back to a very similar curve again. But there are architectural advances that you can begin to think about when you stack memory closer to the processor that you couldn't think about when it was across a memory bus. And those are quite exciting, and why we stand up and say, hey, we need some real government investment for HPC because the commercial trends are pushing us along this path, but it's not good enough to overcome, and make these breakthroughs that we need at the very highest end. And I think, there's pretty much consensus around the economic impact of the applications areas that we can have with Exascale that would justify, these large investments. So I'm fairly optimistic that, there's a convergence of technology shifts, technology challenges, economic impact to the applications, and willingness of governments to listen and say that the industry alone won't do this.
Yeah. So I was wondering, Yutong, is there any technology developments in China concerning memory technology that could be helpful for supercomputers in the future?
Yeah, I think memory is a very important part of the supercomputer. In fact, in our experience, the memory is also the 1/3 of the whole system cost. So in the exascale systems, the memory amount is very large, maybe 10 petaflops to 20 petaflops memory. So I don't know what the exactly right technology for memory, but I think the power, I mentioned as the Mark, the power and the bandwidth and also the latency is very important. So I hope in China now, we might have some companies or institutes to put efforts to do the exact research on that. At least I don't know. Yeah.
Chris, any thoughts?
Well, I'm not going to say anything about technology. I'll say something about algorithms, which, after all, you need to make the technology happen. So you mentioned before I worked in automatic differentiation. Automatic differentiation is a technology that, among other things, in specific instances, requires you to let a program run backwards, as strange as this may sound. So you have to reverse course. One way you can do this is you store everything that you did going forward, and then you have your way back, like Hansel and Gretel walking in the woods and dropping little pieces along the way and hoping nobody eats them. So, but there's an alternative, and this would mean you need lots of memory, okay? There's an alternative which basically says, well, you stop a few crumbs everywhere along the way, and when you have to retrace part of the way, you go back to the last crumb and recompute. So I think part of the answer is we also have to look at algorithms that store less and recompute more. And this is a paradigm shift, because till a few years back, we had plenty of memory. Memory was not the concern. Yeah. And that's something that we have to think about. And there's examples. A physicist colleague of mine in Darmstadt, he has developed a very successful algorithm that is based on that paradigm and allows him to compute what he cares about now much more effectively, because the recomputing can be done on GPU extremely fast. So, and this is something we have to educate our students and to think along these directions. Consider that trade-off rather than just say, well, I store it and I save it.
Right, and look at higher order algorithms in order to get better accuracy out of the memory locations.
For example, that's another,
Right.
I'd like to get you another precise answer. So we agreed that the first exascale platform will be this fabulous molecular dynamics computer. Yeah. So how much memory shall this system have? How much will be affordable?
Yeah, well, that's a very interesting question. That's a very so it's a
it got to do something else but molecular dynamics.
Yeah, agreed. But the more the better. You mentioned that memory is about 1/3 of the cost of systems, and if you want to keep that price balance and also the power balance associated with that, it will probably go down. The B to F ratios probably go down probably 100 petabytes to a couple hundred petabytes on a exaflop machine, can be expected. And again, that's the base roadmap without exascale acceleration investment by government entities. Say it again, there are low-hanging fruits in the memory, the way that memory is designed, 15 or so years ago at the beginning of the CMOS era, that could be redesigned to achieve much higher densities, much lower picojoules per bit transferred and all that kind of good stuff. But it takes a coordinated investment across both CPU and memory. And that was the first thrust of Fast Forward, by the way. So in terms of the DOE, looking at long lead time items, that is to their credit.
So any?
How many memory?
How much memory?
How much memory? I think we can do a calculation of the system, the whole system scale. For the exascale, we do the estimation about the whole system node, maybe 1 million. If we have 1 million nodes, how much memory per nodes? If we have 10 gigabytes per node, it's 10 petabytes. So 10 gigabytes, I think at least we need that. Because if we have 1 million nodes for whole system, so one node at least 1 teraflops. So, so the whole system maybe more than 10 petaflops. So you can calculate it.
So we definitely will look at lower memory systems, no matter what. That's clear. I actually, in preparing for this chat, I looked back, and it turns out that the first town hall meeting in the US on exaflop computing was in April 2007. April, May, June, there were 3 town hall meetings which started all this. This seemed to be really amazing to me that it has been already 5 years that we've been talking about exaflops. Yeah. So it almost seems to me that we've been talking about it for a long time. So what actually has happened in the last 5 years since 2007 that got us a big step closer to exaflops?
I think we understand the challenges and the problem areas much better, and the interrelationships between them. There's a very tight coupling between the applications that need to run, their memory footprints, characteristics, and the hardware-software trade-offs that we're going to have to make. And we talked about memory being a trade-off that will go down. So this whole idea of co-design now has emerged as a thrust area for exascale development, where you're looking at hardware, system software, and application design all together. And that's a fundamentally different paradigm than we did in the petascale era. So not only do we understand the problem better, but we, I think, have very systematic approaches to address the challenges. And as I've mentioned, there's a major effort in Europe, there's a major effort in China, and now the U.S. effort is taking off as well. And I think there's interest in other countries, including India, and it's amazing how much worldwide attention now is being paid to HPC.
Any thoughts about progress?
Yeah,
I mean, there was lots of progress in China in 5 years.
Yeah, that's amazing.
So absolutely,
in
that
China,
should be easy.
It's,
yeah, can you keep that slope going?
I'm not sure about that, but China, the government delivered the project every 5 years, So now, until now, we have expected to the concreted project at the end of the 2015. And after that, it's a 13 5-year plans. So I am not so optimistic about about the year 2018. I think at least in China, maybe around the 2020 year. So for the exascale computing, we still encountered so many issues, problems. I think the most important thing maybe still the system architecture. So I recognize that the programming issue is very important, but I think the most important is we should to find or to through some research to find some feasible system architectures which can deal with the power and the performance and scalability and stability in the limitation power consumptions. Mm-hmm. So if first we should have this machine, the system, and then we consider about the programming. So I also think the core design is very important. But in my experience, some things maybe it's not very exactly to express my my view. But the thing is, hard to use is better than nothing to use.
Yeah.
Well, that's a good lead-in.
Yeah.
What do you think about that, Stephen Cruz?
Well, I mean, it's a sporty attitude, I give you that. But let me actually come back a little bit on that issue of co-design. I mean, this is I think a thought change that also has happened driven by Exascale. And yeah. Certainly, I mean, I grew up, you had a machine, and then you started programming towards that machine, okay? And then you get a new machine, and then you either wrote a new program or tried to get your old program to run on that machine. So to some extent, the architecture, the machine was the fixed point. And I think that can change now. Certainly, if you go a step down from the exascale and look at sort of petascale type applications or even below that, you can now get to the point, I think, if you have an idea and you want to have an architecture, you can have somebody build you an architecture that pretty much suits what you need out of commodity building blocks. And we see that because there's a tremendous amount of diversity, for example, yeah. being offered here on the floor. So I think, to me, co-design, which was before very much focused on hardware, I think you can actually now turn things around to a degree. You can say, I have this algorithm, it has these characteristics, I need a machine that supports that effectively, and you can actually then get a machine that supports that effectively at a moderate cost. It will not be a completely new design that costs you a ton of money. So I think we have more architectural freedom that has been fueled by the race towards the exascale, which I think is a good thing for anything below.
I want to explain more about my view.
You want to explain better hard to use but not to use?
No, it's a worst thing. I think maybe it's related with the programming model, except the MPI Power X. I think it's actually some part of our work now. It's the domain-specific application programming framework. Yeah. It's could be let the scientist, application designer, and the system designer focus on their own priority. So the scientist is application designer could focus on the science model, simulation model, and the system software designer and the hardware designers will focus on the low level, the simulation model mapping to the real architecture. So this is also the application programming framework could become a natural core design platform. Yeah, so I think maybe this way is to the architecture designer that can design their own creative architecture. I still think it's most important, and also we the system software designer and also the application designers could co-design with the framework. Yeah.
Okay. I still want to get some response to the better hard to use than not to use topic. Are things getting easier to use or harder to use? Let me ask this way. I mean, I sort of got the impression that that's actually we're at a point where things are actually getting more difficult instead of easier because of a wide variety of approaches to how the nodes will be programmed, and that there's no agreed on node programming model, for example.
Well, yeah, my view of that is that there are typically periods of innovation and experimentation, and a lot of new ideas go out and are tried out, and some end up being left by the side of the road as we go forward. But that energy and excitement and innovation, and it is very important on a periodic basis to re-energize the community and to get breakthroughs and move us forward. So, but I do agree with you. In the last 5 years or so, there's been a re-energization and diversification of ideas, particularly around the GPUs. But I think that era is kind of coming to a close, and we're seeing that that's a little bit harder than we really want. And if we can maintain the programming model that we had before, that would be a heck of a lot better. And we still have this long-range problem of a million core, a million processors, and a billion-way parallelism that we have to focus on in the next 10 years. So I think there'll be a settling out and then another period of innovation as we enter the exascale era.
Okay. Any thoughts about current program? No? Chris?
No, I think I agree with what you said. I think it's at the moment it's gotten harder to program parallel machines because you have basically 3 levels of parallelism you try to address. You have distributed memory parallelism, you have shared memory parallelism, and you have vector type parallelism.
Yeah.
And you have to balance these balls correctly. And when the killer micros first came around, it was just distributed memory, so life was easier.
Yeah, absolutely.
So, to get a simple yes or no answer, we'll use MPI on the exaflop machine.
Definitely, it'll be available and applications will use it.
Okay.
Yes.
Yes. Okay. Agreement.
Yeah.
That was easy. Related to this, I asked you to think about this question, and it's a little bit a longer question, so you can take your time to answer it. When do you think the first exaflop machine will actually appear on the top 500 list? I know Hans is very anxious and says it will be in 2019. By extra, it will be. Now let's have the experts go at it.
Does it still make sense to answer the question? No.
Will it be?
I think it's 2018 to 2020, 21. Is in time frame. It depends on the investment that governments are willing to make. I think you said earlier 2020 is probably likely for China.
Yeah. 2020 we'll have an exaflop machine in China built by you, maybe.
I'm not sure.
I'm not sure about that. Yeah.
Really.
Chris.
I think it's a good timeline, assuming there's no major economic disruptions, because it'll be an expensive machine.
True. So before 2020, what? Maybe I'll make this precise. When will there be the first exaflop machine in Europe, so you can focus on the European issues to sort that out?
Which puts that sentence that I said before particularly in focus. But anyway, no, I would say I think within Europe, I mean, with the PRAISE project, also the EU funding, I think the European community has understood that it's important to push, to push supercomputing as a capability. The question is, can the EU get to the point where they fund one side to build that machine? Because the distributed model that we've had so far, for example in PRAISE, where you have 6 or 7 sites chipping in each a quarter of their cycles to provide an environment, that doesn't work there. So there has to be one site that provides it. If I were to venture a guess, then if Germany is doing well, they might do it, but it'll probably be a little bit later, simply to have the costs driven down. So I'd say 22.
Okay. And we actually, concerning the site, we heard yesterday that best would be to put these machines at the Arctic Circle or further north. So Norway, Sweden, Finland maybe have a better and Iceland might be
free cooling. The question about who pays for them, okay, that maybe is, I think is the really critical one.
Yeah. Well, I want to ask you a last question, and the last question is the bonus question because you're not prepared for it and you don't know what it is, but it's an easy one. So suppose I'm your magic fairy, and I'll grant you 3 wishes. To remove any barriers on the way to Exascale, what would you like to get done by tomorrow through magic? What's the toughest problem that keeps you busy thinking? Life must be easy. Any thoughts?
Yeah, well, only 3, huh?
No, only one. One each.
Oh, one each. Oh, okay. Well, let's see.
But you can cooperate.
Yeah, maybe we should commit on this. So, power scaling and resiliency are what keep me up at night. And it's not just, on the system itself, but it's also in the I/O subsystem, because they're not.
So that's 2.
Yeah. No, I haven't told you what my wish is.
Oh, that's what you wish.
Yeah.
I thought your wish is to have absolutely perfectly always functioning 0 error.
Oh,
hardware.
How did you know? That was going to be my wish.
That was your wish?
Yeah.
Okay. Well, I'll give you another one.
No, that was too. No,
that's good. Do you have any wish for the future?
I have so many wishes. So all in one, I think. I wish tomorrow Exascale computing emerges in front of me.
Okay, that's too easy.
Yeah, too easy. Yeah.
Well, it's a good answer, but it was easy. Chris?
Well, so for me, it's really the software issue. Okay, what I'd like to have is a software that I can write easily and compose, and it runs on an Exascale machine and gives me decent performance. That's like you mentioned before, app program, right? Yeah. So if you look at these programming environments, there's a rich set of libraries that you have. You can plug them together, they work, and you can quickly deploy software and experiment. And that's what I'd like to be able to do. Use these great computing devices to do experimentation, but without having a multi-year ramp up to try out a new idea that maybe only makes sense because you can do it on a petascale computer. So I look at these not as petascale, exascale computer. I look at these as enabling devices for new thoughts, not just as an evolution of where we are now. And that enabling factor rests on software, and it isn't quite there yet where I'd like it to be.
Okay, so the magic software bullet.
Yeah, something like that. Yes, the magic software one.
So in thinking, I would like to come back to my wish.
Good.
No, so
we can deal with errors.
Yeah. So assuming we can deal with errors, I would really like to see the democratization of HPC. And one of the really exciting things about working at Intel is, we've been thinking a lot about this missing middle and how to address that marketplace. And, what has occurred to us, and Raj mentioned this yesterday in his keynote, is that, if you get an exascale in 20 megawatts, you get petascale in 20 kilowatts. And that's about a rack or 2, of stuff. Yeah. And all of a sudden, things that are, in the top 10 or top 20 of the top 500 list are affordable as a departmental supercomputer, and I'm going, holy cow, the science you can do with that is going to be breathtaking. So,
indeed.
So, what I hope for is that we at Intel can figure out how to, commoditize and push the exascale technology out, to a broader community.
Well, I think since this was a chat among us and you had the opportunity to listen to our chat, I'm not taking any questions, but I'd like to have some audience participation in thanking my guests for their insightful comments and the entertainment that they provided for the last hour. So thank you.
Thank you.
Thank you, Mark.
Very good. Good questions. Thank you.
Thank you.
Thank you very much. Yes, thanks very much.